Good afternoon, everyone. Today we have the pleasure of having Donald C. Dilworth with us as the colloquium speaker. He received a BS from MIT in physics in 1961. Don is president of Optical Systems Design Inc. and has since 1961 been intensively involved in development and application of computer software for optical design. He has extensive experience in most areas of lens design, particularly in thermal infrared systems, and is the author of the well-known SYNOPSYS lens design program, which is widely used by lens designers worldwide. As author of SYNOPSYS, Don has advanced the state-of-the-art in the areas of artificial intelligence, and with the development of the popular Pseudo-Second Derivative method, he was a senior principal development engineer at the Honeywell Radiation Center, where he was responsible for conceptual and detailed design, tolerancing and analysis of numerous IR and visible light systems, including star trackers, periscope optics, and FLIRs. He was director of the optical design department at Bose Optics Incorporated, where he developed and implemented techniques for the design of geometric and thin films optics. Prior to joining Bose Optics, Don was employed at iTech Corporation as senior optical physicist. In this capacity, he was responsible for designing a variety of advanced optical systems, including aerial photographic lenses used on the recently declassified Corona project, aspheric systems, multi-layer dielectric coatings, and a submarine periscope. At MIT, he developed computational techniques for optical and thin film design, which were applied to the design of the optical navigation equipment for the Apollo project. Knowing him more personally, Don is an exceptional musician, an accomplished musician. He also is a painter. And we have with us today a very bright mind. With this, Don.
Well, thank you, Jose, for that generous introduction. I want to thank the university for inviting me to come here. The occasion is I've granted the university an educational license for the use of my lens design program, which is called SYNOPSYS, which is the real SYNOPSYS, and it has nothing whatever to do with a company called SYNOPSYS that sells a competing program, which I won't even name. I'm going to give a rather rambling and wide-ranging talk dealing with optics in various ways. Some of the personalities involved, the history, some of the conflicts. And let's start just with talking about lenses and optics. How many of you remember the very first optical lesson you ever learned? Well, I remember. How old were you when you first discovered the mirror? Now, it can be shown mathematically that a plane mirror is the only perfect optical system. And they've done some fascinating experiments. They will put a mirror up next to a chimpanzee's cage or an elephant, and they found the animal very quickly learns that that's not a different animal in the mirror. It says, that's me. The animal learns that he's looking at himself. Well, in the picture here, that's me. I was about 2 years old, and the family was visiting some friends in a big old house. And like any bored child, I was walking around exploring. I climbed some stairs and found myself up in the attic. Oh, what an interesting place. And I was walking around, the furniture and boxes piled up, and I was exploring. Now, up against one wall was a large mirror. And as I walked across this attic, out of the corner of my eye, I saw a little boy up there. I said, oh, that's interesting. There's somebody else up here. And I started looking around for who this other person was. And I couldn't find him. I thought, well, maybe he's hiding. And I was looking behind the boxes and getting kind of frustrated until I guess I can't find him. And I walked back towards where I started, and there he was again. And then he wasn't there. What's going on? I'm only 2 years old, remember. And then I thought, well, I saw him when I was over there, so I went over there, and looked, and there he was, a little boy looking at me. And I walked up toward him, and he walked up towards me. I moved, and he moved. I remember looking at this kid and saying, what a cute kid this is. And it looked like Charlie Brown, a big head, big blue eyes, blue overalls. And then I realized, hey, that's me. You know, it's reassuring to know that I was as smart as a chimpanzee. You know, we all start out cute, but then something happens. Well, that was my first optics lesson. I was standing there looking at this little boy, realized it was me. I blinked and I saw the eyelids quiver. Oh, that's interesting. I blinked a few more times and the eyelids quivered. And then I got curious. I wonder what I look like with my eyes closed. So I closed my eyes. And I couldn't see anything. So that was my first optics lesson. Now I'm enjoying a wonderful career in optics. And partway along the way, I made a little lens grinding machine in my basement. You wiggle this bar, and the spindle turns, and you can make lenses. And this shows this way of making lenses is not much different from what they might have done in the Middle Ages. A professor at MIT named Philip Morrison heard about this, and he asked me if I would participate in a television series that he was doing called The Ring of Truth. Some of you may remember that, and there's a book that came out. This series explored the question of how does science know what science knows? And in one chapter, he talks about lenses and telescopes and so on, because that was important in the history of science. Well, let's talk about lenses. Where the heck do lenses come from anyway? And here's a very hypothetical situation. Here's a nearsighted youth. You can tell he's a youth because he's riding on a skateboard here. And he's looking through a window. Now, this is in the Middle Ages. And window glass in that time wasn't real good quality. It's full of bubbles and things. And this kid finds that if he looks through a big bubble, he can see what's on the other side of the window more clearly than if the window weren't there. Because if you look at it, the inside of this bubble here makes a nice negative lens. And that's exactly the kind of lens they want to prescribe for somebody who's nearsighted. So presto, the negative lens has been discovered. Okay, here's a far-sighted old codger. He can't see things that are up close, but he discovers if he looks through the bottom of a beer bottle, makes a nice positive lens. Now he can see what he's looking at. So the positive lens is invented. Now, I can't claim this was actually how it happened, but it could have happened this way. Anyhow, now we have lenses that were invented. And we know that spectacle lenses were in use from the 14th century. This is a monastery in northern Italy. And if you look up here on the wall, there's a fresco going around with 40 monks all painted at their desks, copying manuscripts or whatever monks did. And one of these monks is shown wearing glasses. Now, this is the first picture in all of Western art that shows eyeglasses. And in 1306, a priest wrote, it's not 20 years since glasses were discovered. So we know that about this time, eyeglasses had been discovered. Now, in those days, if you wanted glasses, you went into the optician's shop, and he had trays of lenses out on his tables, positive, negative, weaker, and stronger. And you'd pick these lenses up and look through them, and you'd, just by trial and error, you'd find two lenses that you liked, and so you'd buy them. He'd mount them in a frame, and that's how you got your glasses in those days. Well, it doesn't take much imagination to think that sooner or later somebody's going to pick up two lenses and just say, what the heck, what happens if I do this? And so all of a sudden, we have the telescope invented. It was probably invented many times. Here's a curious youth. He's picking up lenses. This little kid has just invented the telescope, but he doesn't know it's important, so he doesn't tell anybody. And his mother says, Billy, put those lenses down and come home. Well, this combination must have been discovered many times. And we can then ask, well, who actually invented the telescope? And here's our first controversy, because many names have been suggested. Historians have named all these. And in fact, there was a lot of controversy at that time, because some of these people were suing each other, claiming, I'm the inventor, no, I'm the inventor, and they tried to get a patent, and it was challenged in the courts. So there was a lot of conflict way back then over who invented the telescope. But here's something interesting. This is a document written before 1570, where he says, "My father, by his continual painful practices with proportional glasses duly situate, discovered things far off, and 7 miles off declared what hath been doing at that instant in private places." So here's, in the middle of the 16th century, we assume the telescope has already been invented. Word reached Galileo, who wrote, "About 10 months ago, a report reached my ears that a Fleming had constructed a spyglass," and so on. And then Galileo, being a very smart guy, had no trouble in quickly figuring out what kind of lenses would make a telescope. Okay, that's Galileo, bless his heart. And this is the kind of telescope that he discovered independently. It's called a Galilean Telescope, obviously. And the way it works is this. Starlight comes in here from the left. It focuses down. But before it comes to a focus, you stick a negative lens there to straighten the light rays out again. Now it turns out the ratio of the beam diameter at the front to the beam diameter at the back, that ratio is just the magnifying power of the telescope. It's a simple design, but it's got a serious problem. That's this. If you try to look at something that's a little bit off of the center of the field, the light that comes out is aimed away from your eye, and you can't see anything except in a very small field in the middle. And that's the problem with the Galilean telescope. Let's go to Johannes Kepler, who invented a better telescope. And he also calculated the orbits of the planets. And it's staggering to think of the amount of labor that poor guy must have done. You know, this is before computers. He's doing things by hand. He would assume that the planets had a certain shape orbit, and then he would calculate longhand where that planet would appear in the sky, say 6 months ago or a year ago. Then he would look up the charts, because astronomers had been measuring the position in the sky for generations. And if the two positions didn't match up, he'd throw all those calculations away, assume a different shape, and do it over again, and over, until he almost went mad. And when he got around to assuming an elliptical orbit, then the numbers matched. Now he knows the shape of the orbits of the planets. And he also invented a better telescope, which is called, of course, the Keplerian Telescope. And it's made by a little different principle. It's a longer telescope. You let the light come to a focus, and you put a positive lens on the other side to recollimate the light. And this has the very nice property that it aims the light into the eye instead of aiming it away from the eye. So the field of view is much larger. And here's a letter written sometime around 1660, which says, "The Galilean telescope that he observed with were made with a concave glass next the eye, and they take in but a little compass. And if they're made with convexes and never a concave, they'll take in 40 times more of an object." So here's a document from the middle 17th century describing the Keplerian telescope. Now we can ask, why did Galileo not discover the Keplerian telescope? And the reason is, by trial and error, using the lenses that were in the optician's shop, there was no combination of lenses that would make a Keplerian telescope unless you hold it a long distance away, and of course then your arm breaks in the middle. So no one discovered the Keplerian telescope just by trial and error. It took Kepler with his brains to figure out how that would work. So lens design in those days was a trial and error business. Galileo said you could get 5 or 10 pairs out of 100. There was no lens design. It was just trial and error. But some combinations were actually quite good. I have looked through an authentic 17th century telescope, little bitty Galilean thing, and for that telescope the image was sharp. So occasionally they got a real good one. They usually had to stop down the objective. It's small anyway, and they stopped it down even smaller because that would make a sharper image. I thought this was interesting. This is a price list for lenses from 1647 written in Latin. I'm sure none of you have ever seen something like this before, so this is your chance, okay, in Latin. Can you read it? No. Here's some of the early telescopes which they made with the early lenses. They're real pretty little things. In fact, going through the museum here in the Optical Sciences Center, they have examples of some of these, which are really interesting. And here's a picture of Galileo's original telescope. Now, these are little bitty things, but in spite of that, I would say these humble telescopes are the most important scientific instruments of all time. Not because of what they discovered, because, after all, they are pretty small. Instead, they're important because they set Europe on a path toward rational science. Now remember, this is happening at the end of the Dark Ages. The Inquisition was raging all over Europe. They were burning people at the stake. If you didn't believe what the church told you to believe, they set you on fire. And one of the things the church told you to believe was the idea that truth comes from revelation. And Galileo said, no, no, truth comes from observation. And this is a fundamental difference. In fact, that statement alone would have got him burned as a heretic, because that was already heresy. And as a controversy that goes way back, thousands of years, way back to Plato and Aristotle, actually. Aristotle, you might remember, taught that the way to understand the world is to study the world. Sounds pretty sensible. Plato said, no, 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 you can't do that, because everything in the world is imperfect. Therefore, the way the world appears to be is not the way the world really is. And if you want to understand the way the world really is, you just have to sit there and think about it. So that was the big dichotomy, which has been coming and going for thousands of years. Galileo brought it into focus when he said that the way to the truth is through observation. And he didn't stop there. He discovered the moons of Jupiter. And oh boy, was he in trouble now, because one of the things the church was teaching was that the earth is the center of the universe. And their way of thinking was very simple. The most important part of a circle is the center. We humans are the most important thing in the universe, therefore we must be at the center. This passed for logic in those days. And Galileo comes along and says, hey, there's another center out there. Oh boy, was he in trouble now. And of course, the story is well known. He was tried by the Inquisition. He was convicted. They couldn't burn him at the stake because he had too many important friends, so they just forced him to recant, and he spent the rest of his life under house arrest. It's a black mark on the history of civilization. But what's ironic is that Galileo wasn't the first to discover the moons of Jupiter. It turns out Arab astronomers had already found 3 of them. Now, at this time, the Dark Ages in Europe, this was a period of great flowering in the Arab countries. They had art, they had literature, they had mathematics, they wrote books, they had libraries. Our word algebra is an Arab word. The stars Aldebaran, Albireo, those are Arab words. But none of this information made its way to the West, because in that period, the West was busy burning books. Anything that showed up that disagreed with the Bible, well, that was it. They would burn it. So they didn't find out about the moons of Jupiter. And here's something even more interesting. One of the editors of Sky and Telescope magazine, named Talman Tal, has written a piece saying that his daughter can see the moons of Jupiter with her naked eye. I suspect children have been seeing them for centuries, because the pupils of children's eyes are larger than adults, and if they have perfect vision, they can see the moons of Jupiter, little tiny things right next to the planet. But children, being so sweet and innocent, they don't know it's important, so they never told anybody. But Galileo knew it was important, and he told people, and he got himself in a pile of trouble. It conflicted with Orthodox clergy. But more than that, it also annoyed the intellectuals. A lot of people not connected with the church didn't like Galileo, because nobody likes to be told that things he's believed all his life are not true. Now, about this time, Galileo discovered the strange shape of the planet Saturn. Now, he couldn't really see it clearly in his teeny little telescope, but he could see the disk of the planet, and it looks like some little doodads on the side. He didn't know what they were. So he sent a coded message to his friend Kepler. Now remember, this is in the Inquisition. You don't just announce scientific discoveries, right? So he sent it to Kepler in code. And the code was this. It's an anagram. Here's the Latin phrase that was what he really meant, which means I have observed the highest of the planets 3 formed. Now Kepler, bless his heart, decoded it all wrong. He came up with this, which means be greeted, double-knobbed children of Mars. Now, we think that's very amusing, but there's actually a dark side to this story which has not been explored by anybody, and I think it should be explored. We can ask, why did Kepler accept this faulty translation? It turns out there's one letter wrong in here. I don't know which letter, but surely Kepler knew that there was one letter wrong. And yet he accepted this explanation, and we can ask why. And the answer points to something in human nature which is not very pretty. You see, Kepler believed that because Kepler wanted to believe it. At this time, before there was science, there were other things like numerology. And those people had their own logic. And they were saying things like, well, the Earth has one moon. Jupiter has 4 moons, which is all they could see. And Mars, which is in between, well, it must have 2 moons. And this idea was current. It was spread around. It was believed by many people. When Jonathan Swift wrote Gulliver's Travels, there's one chapter when he talks about Mars and his 2 tiny moons. The historians went gaga over that. How could they have known? It was centuries before our telescopes were big enough to see these moons. And the answer is, well, they didn't know. It was what we call pseudoscience today, just numerology. And when Kepler got this translation, it looks like children of Mars, those must be moons. Double knob, it sounds like 2 of them. In other words, this faulty translation confirmed what he wanted to believe. And this is a facet of human nature which is called confirmation bias. And the way this works is, if you want to believe something and you see evidence that supports that belief, you don't pick that evidence apart, you don't question it, you don't try to prove it wrong, you accept it. But if you see evidence that contradicts something that you want to believe, then you pick it apart and try to prove it's wrong. This is a bias. It's in every human being, it's part of human nature, it's in me, it's in you. Because it has caused so much bloodshed and anguish for so many centuries, I'm always on guard against that tendency in myself. I wish everybody was, but most people are not. Kepler was not, and that's why Kepler accepted this translation. Okay, Kepler discovered the shape of the orbits of the planets by this very laborious method. Isaac Newton came along, probably the greatest scientist who ever lived, and with his theory of gravity, he proved mathematically that the orbits have to be ellipses. Now, in his laboratory, he had samples of many kinds of optical glass, and he would grind them into prisms, send sunlight in, and measure how the spectrum is spread out. He made very careful measurements, and he discovered for all the glasses he tested that they diverged the prismatic colors in a constant proportion to their mean refraction. Now, if that were true, that would mean that it's impossible to make a color-corrected telescope, and Newton knew that. It turns out in his laboratory there was a piece of a kind of glass which we call flint glass, but he never got around to making a prism out of it and measuring it. If he had, he would have seen that here was a different proportion. But he didn't know that, and therefore he thought the only way to make a telescope that didn't have a lot of color problems was to make it a reflecting telescope, and that's why he invented that. Here's an example of a reflecting telescope. This is made by Sir William Herschel. And this is the telescope that first showed the planet Uranus in 1781. Now, there's a mirror at the bottom. Starlight comes in, is focused by the mirror up near the top, where there's an eyepiece where you look at it. The reflecting telescope was then improved by Laurent Cassegrain. Here's an article in French showing his convex mirror, and it goes back through a hole in the primary. Here's an interesting picture I came across. This is from 1685, showing one of the telescopes available at that time and the different kind of lens arrangements inside. It looks like one of these has an erecting system, because the Keplerian Telescope makes an upside-down image, but they've put another set of lenses in, and it turns it right side up again. This is the first permanent scientific photograph ever taken. It's a daguerreotype by Sir John Herschel, showing his father's 40-foot reflector. Can you imagine seeing that monstrosity up on a hill, all made out of wood, with a 40-foot focal length reflector? That's what telescopes used to look like. And controversy is still with us. In my own field of lens design, I can point to 2 schools of thought. One was the English school, which espoused lots of algebra. You want to understand your lens, do lots of theory. You don't trace very many rays. Instead, you build the lens according to your theory, and you measure the image. And then you go back and you iterate. Contrast that with the German school. They did some algebra, but then they wanted to trace rays and find out where the light really goes. And they would trace and trace and trace. They wanted to get it right before you make the lens. Now, there were strong opinions in these 2 schools. I put these into 2 camps, the theorist and the number cruncher. Okay, the theorist wants to do all kinds of algebra, understand the lens before he builds it, and then build it. The number cruncher wants to say, before you build it, trace lots of rays and find out where the light really goes. Okay, this is the dichotomy we had here. But now here's something interesting. Before you can apply either method, you need some laws. This is a reproduction of a manuscript from 984 by an Arab. This is in Arabic, which shows that they had already discovered Snell's Law way back then. Now, this was a period in the Arab world, I told you, that of great flowering of culture, but none of that reached the West. So we give credit to Thomas Harriot, also Descartes, Fermat. Snell's Law was actually discovered by many people. Snell gets the credit for it. But here's another controversy showed up. Both Fermat and Huygens accused Descartes of copying Snell, and there were recriminations, articles in the paper condemning them. There was a lot of nastiness about that in those days. Turns out Descartes was innocent. He derived it completely independently. But that was a controversy in that era. Now, once you have Snell's Law, now it's possible to outline a set of equations you go through, and you can trace a ray, and you can find out where it goes. And they use the number crunching which they used to look like this. You'd make a chart, first surface, second surface, third surface, go through all these calculations using log tables. Can you imagine the labor of doing that? And eventually find out where the ray winds up at the image. Now, all this is only possible because Jean Napier had already invented logarithms. But keep in mind, you need more than just the invention of logarithms. You also need tables of logarithms, and those had to be calculated by hand, year by year, getting thousands and thousands of values before you can actually use logarithms. So this whole thing sounds like a very tedious endeavor. And so people wanted to do it with an algebraic approach. Seidel came up with his aberrations in the 19th century, which said with a moderate amount of algebra, goes on, looks like this, you can get an approximation to the way a lens would actually perform. Problem is, it wasn't too accurate. We say today it's a third-order theory, whereas in any reasonable lens, any challenging lens, there are higher-order aberrations which are much more important, or at least equally important, and the third-order theory doesn't tell you anything about that. So any lens you calculate based on third-order theory is not going to work all that well. And to try to make the theory work better, people have tried to develop this, higher orders and higher orders, and they developed the algebraic approach to the point where it became so ponderous and so unusable it collapsed under its own weight. Here's a page from a book by Arthur Cox. Imagine 665 pages, most of which look just like this. Now, I don't want to disparage the late Arthur Cox. He was a scholar, highly respected, and he deserves respect. But nobody's going to charge through 600 and some pages of algebra in order to save some time tracing rays. And there's a guy named T. Smith who was actually even worse, if that's possible. He wrote some papers with his theory of lenses. I got one of his papers once. I said, I'm going to learn this stuff. I mean, this is a smart guy. Let me see what it says. And I studied this paper. And I studied it day after day, line by line. What is this guy doing? And I couldn't make heads or tails out of it. And later I was talking with Rudolf Kingslake. I said, Rudolf, what do you make of these papers by T. Smith? And instantly he answered, they are utterly incomprehensible. Which made me feel good because I thought I was pretty stupid there for a while. And then he added, and he does that deliberately. Now, there's an interesting problem. Why would a very smart guy write very complicated papers with the intention that nobody can read them? Now, that says something else about human nature, which is not very pretty. And I'll let you speculate on that as well as I can. Okay, so this controversy has been playing out for a long time. Ray tracing was very tedious, log tables way before computers. So designers resorted to algebra, which can be incomprehensible and doesn't work very well. And here are some illustrious opinions. This is Max Petzval, the famous, he invented the Petzval lens. He was a number cruncher from the German school, professor of mathematics in Vienna. He, in order to design his Petzval lens, he wanted to trace lots of rays, and it was so tedious he had to get help from artillery gunners because their job was to calculate the trajectories of cannonballs. So they were good at doing math. So he got Petzval, a corporal, and 8 gunners. Took him 6 months to trace enough rays to design 2 Petzval lenses. That's an example of the German school. Ernst Abbe, another German, He had a rigid rule that the design and computing must be finished in the computing office without any recourse to workshop trials. The German way, trace lots of rays. Now contrast that with the English procedure. Hastings is a good example. Make the lens and test it. Now when they used theory, of course they were using third order theory, which isn't very accurate, and he knew that. So he acknowledged no objective had ever been constructed under the guidance of theory alone. Now that's an honest opinion. And none ever would be so made, he then said. Experiment alone could be expected to serve as an infallible guide. That was the English way. And here's another famous name, H. Dennis Taylor. And I love this picture. If ever there was someone who looked like a stuffy Englishman, that's it, right? And he's sniffing at these foolish Germans. The German workers, they tested by exact rate tracing by trigonometrical methods. It's a needless waste of both time and working costs. So there was some controversy across the English channel, the English method and the German method. Lots of algebra. Think like crazy. Make the lens and measure the image. That was the English way. A.E. Conrad, now we have a 20th century expert. He wrote some books which use the best technology, I think the best of both schools. He is widely considered the father of modern lens design. He was also the father of a little girl named Hilda, who grew up and married Rudolf Kingslake. And this is Rudolf. And I think Rudolf also had one foot in both camps. Of course, he was a professional long before we had computers. And he commented nobody had ever traced a skew ray before 1950, except to show it was possible. When someone applied for a job in Kodak, he'd ask him if he can press the buttons of a desk calculator for 40 years. If he said yes, I'd hire him. That's what he wrote. He also said something which is kind of disturbing. It was at a convention. We were giving papers on computer lens design. And he got up and he said, "We are losing the ability to design a lens through an effort of the intellect." Now, that's a true statement. That's kind of disturbing. And that there's a lot of deep thought that has to go into analyzing that. Here's an example of Kingslake's method. He would look at, say, spherical aberration. He'd change a radius, make another plot, and change the thickness and look at coma. Plot some curves, see where they cross, and over he'd figure out how to make what shape the lenses should be in. And I thought, when I saw these things in his book, I said, gee, there's a lot of fundamental insight in there, and I would like to know that, because I don't know how to do that. So one time I was talking to Rudolf, I said, in your book, when you say you're going to change this radius and look at spherical, and change this thickness and look at coma, how did you know that this radius would affect the spherical and this thickness would affect the coma? Because that's the insight that I wanted to know. And he said to me, that's the only thing that worked. I tried everything else. In other words, this insight that I was hoping for wasn't really there. Even the experts were reduced to trial and error to a large extent. So what's the conflict today? Well, brains versus brawn. Here's an inspired genius who can understand lenses so much that he knows just how to, what they should look like. And on the other side is a nitwit with a fast PC. He can push a button, come up with a great lens, and he doesn't have a clue what happened. And these people exist, trust me. Today we're still in two camps. The one camp says algebra comes first. We are losing the ability to design a lens through an effort of the intellect. And the other camp says we have lost the ability to make flint arrowheads and ride horses too, and who cares? Because we don't have to do those things anymore. The one camp says you must understand your lens. The other camp says you must understand your optimization program. And the one camp says, I can design a 5-element lens in only 5 days. And I actually heard this. I know someone who teaches lens design, and the method used is almost the same thing as Kingslake's method. You know, wiggling a lens, looking at third order, over and over and over. And yes, if you design a 5-element lens that way, it's going to take you 5 days. But heck, my software can design that lens in 5 minutes. Now, why are some people still teaching lens designers these old ways of doing it? There's a book by Joe Geary used to teach lens design. It's more advanced. It's not Kingslake's method. It's more advanced. But he still has them doing a pre-design by hand before you go on a computer. If you want to do a 4-element lens, he says, well, you do a doublet here, you correct that. You do a doublet and correct that. Then you put them together, you know, step by step, a lot of handwork. Why are people still teaching that way? By the way, I wrote a supplement to that book that shows you don't have to do it that way anymore. And I can steer you to my website where you can buy a copy, should you be interested. One reason maybe the teachers need something to teach. And so they're teaching ways that in some cases are really obsolete. I would say we should teach students the fundamentals. So the debate still rages. I would like to see the optics community have some kind of a convocation or something where we really discuss what do students need to know? What are the fundamentals? What should we teach them? I understand at the university they've probably already gone a great distance in that direction. I don't know what the details are. But anyhow, I think this is a debate that's still raging because some people are still teaching the old ways. And I think the community would be better off if we could have this kind of debate and settle on a curriculum. Recently, a customer of mine sent me 10 pages of hand calculations for a zoom lens. Can you imagine doing this by hand, calculating the motions and the powers of these elements? He's a bright guy, but my goodness, my software can do that in a few minutes. See, here's a zoom lens that moves over here and over here and over here. Modern software can do this stuff. There's no reason for a human to have to do this kind of labor anymore. Now, I want to jump to a modern comparison. This will compare lens design using the older methods. Well, lens design using a method where you rely heavily on your knowledge of aberrations, contrasted with lens design using pure number crunching. This was a paper which I gave jointly with David Schaefer at the SPIE meeting in August. SPIE, it means a Society of Photographic Instrumentation Engineers. And I was at a convention. I've given a few papers there. I walked into the convention one time, and there was this rumor going around that a bunch of FBI agents had come in the first day, and they were patrolling around trying to find out what was going on at this spy convention. Okay. This paper came about because it was part of the ongoing development of my global optimization program. I was looking for a very hard problem. The goal was to break the program, because if you want to improve your code, a good way to do that is find out where it breaks. So I contacted Dave Schaefer, whom I've known for 50 years, and he's one of probably the greatest lens designer in the world. And I asked him, send me a very hard problem so I can test my code. And he was happy to do so. And he suggested that we build this as a man versus machine challenge. So I said, we should give a joint paper, and you show how you do it, and I show how the computer can do it. Friendly competition, David Schaefer versus John Dilworth. And Dave suggested that we call it the John Henry Lens Design Contest. Now, if you don't know the story, John Henry is an American folk hero. That's John Henry. And he took part in the original man versus machine contest, where his job was to pound holes in rocks with this big hammer of his. And one day a steam drill showed up, threatening his job. That's the steam drill. And according to the legend, they had a contest, which John Henry won, but then he laid down his hammer and he died. Okay, more prosaically we can ask, can a very good lens designer beat a very good program? And that was the contest. We're going to find out. Now, the first part of the talk was given by David Schaefer, who was not here. So I'll just paraphrase and summarize how he approached it from a theoretical point of view. He played the role of a human in this contest. He noticed that a computer has already won in chess. He can beat a human grandmaster. So we can ask, where are we in lens design? Can a computer beat the best humans? And he wanted to pick a problem where the human would have an advantage. So, okay, I'll let him have the advantage. He picked a lens which he had designed many years ago, used for optical lithography. And the way he did it involved an understanding of the difference between intrinsic and induced aberrations. Now, the way that works is this. Intrinsic aberrations depend on the surface and the conjugates. Induced aberrations are due to the aberrations from previous surfaces. And sometimes they're more important than the intrinsic aberrations. And here's an example. Here's a mirror. The mirror, as you know, reflects all colors exactly the same, so it does not have any of what we call pseudochromatism. But if you put a lens in front of this mirror, Now that lens has chromatic aberration. It focuses colors in different places. That means the conjugate positions seen by the mirror depend on wavelength. And therefore, its spherical aberration depends on wavelength. Now that's an induced aberration. It's not intrinsic. Here's the lens that he had done for the microlithography problem. And he notes that correcting the color in the right place can reduce the induced aberrations elsewhere. This is his fundamental insight. And by using this knowledge, he was able to come up with a good lens without too much effort. These are the specs for the problem, 100 millimeter focal length, NA, and so on. You can read this. It was to work in the ultraviolet at 2 separated lines, and you're only allowed to use 2 different kinds of glass. When he did this, the ultraviolet transmission was an issue, and these were the glasses. So that was the problem. It was supposed to be a hard problem. Dave came up with an 11-element lens that's close to the diffraction limit. He's very proud of this. Then he got curious, maybe can he do it with fewer elements? Well, looky here. He has discovered in his design, he used a negative lens made out of a crown glass. Now, normally when we design lenses, the negative elements are the flint glass. And he found that by doing it the other way, he could change the chromatic aberration going into other lenses and so wind up with pretty good correction. Now, that's a clever guy that can figure that out. He also figured out he could do that with only 10 elements. And he was then surprised he managed to do it with 9 elements. And he said, gee, how far can I push this? And he came up with an 8-element design. And he was as surprised as anybody else that he was able to do this. And then just to see how far he could go, he tried a 7-element. He notices designs can be stuck in a local minimum of a merit function, which makes it hard to do these designs. Nonetheless, he came up with a 7-element design, which was not all that hot. And this is as far as he can push it. So this is what Schaefer did. 11 elements, 10, 9, 8, and then 7, but 7 isn't very good. Okay, that's the human approach to this problem. The next part of the talk is given by the steam drill. That's me. And as I said at the outset, the goal was to break the program, find a real hard problem, and then compare the results. Let me note that a computer cannot solve the whole problem. The customer has to give you the requirements. He usually wants something impossible, so you negotiate. And when you finally agree on what the requirements are, then you select the configuration right here. And once you have the configuration, then you go off and you optimize it. Now, this contest only involves the red part, just selecting the configuration, just so you'll know. And we can ask, can a machine find the best design in principle? Well, of course. If you try an infinite number, you'll always get there. But as Mark Twain said, I want to still be young when we get there. So we have to cut corners. We need some way to generate trial designs. You'd like it to be fast and thorough. And, of course, there's a trade-off there, because if you're more thorough, it's going to take longer. It can't be as fast. So we need a trick. We need some insight to make this thing practical. And here's a way to get this insight. In lens design, what you're trying to do is to find the lowest valley. Imagine a mountain range in about 30 dimensions. Now, if there's a valley over here that's really low, you can't see that if you're stuck in a valley here. And that's why lens design is hard. So how can we do this? How can we find that low valley? Well, here's an insight. Instead of trying a whole pile of designs, go to the top of a hill and look around, and you can see all the valleys. And you slide downhill until you reach a valley. And if you slide downhill in this direction, you reach a different valley. And in principle, if you try all these different directions, you can find all the valleys. Well, that's a tempting metaphor. It deserves to be programmed and tried out. Now, what's an optical hill anyway? Well, plane parallel plates. You've got plane parallel plates. The curves can go either positive or they can go negative. So you can go this way or that way down the mountain. And one way to implement that is to generate a binary number where each bit is an element. That is 1, 0, 1 would be positive, negative, positive. And by trying all values of this binary number, you have tried all combinations of positive and negative lenses. So, hey, that's a neat idea. I've programmed that as a feature called D-Search as part of my SYNOPSYS program, the real SYNOPSYS program. And I note that D-Search is a fast idiot. It knows nothing of aberration theory. When someone like Schaefer approaches a design like this, and he gets an insight involving aberrations, you can't just take that insight and apply it to a whole different problem. You need a new insight. And a commercial program has to work on every problem. So it has to go about it differently. And what it does is almost entirely based on ray tracing. So what can it do? Well, here's some trade-offs. We can either be fast or we can be thorough. One trade-off is you can use a random number, which can be a large number, or the binary search that I mentioned, which is usually a tiny subspace and it runs much faster. That's the RB trade-off. You have the choice of doing a full optimization of each case, or else do a quick screening pass. You pick the winners and only spend time on those. That's the FQ trade-off. And you have the option of doing simulated annealing afterwards. Now, if you don't know the term, simulated annealing refers to the process where when a design has reached the bottom of a valley, you can't improve it anymore, you make a small random change to all the variables and you optimize again. You make another small random change and optimize. And that process can get you over a hill and into a deeper valley. It turns out to be a very powerful tool. I use it all the time. And that's an option. It takes longer, but the results are better. So that's one of the trade-offs. The input to D-Search does not have any starting lens in it. You give it the system specifications, object and wavelengths and so on, design goals, 8 elements, F number. The options you selected, that's the fast and slow trade-offs. And there's a special section where you can say low distortion or whatever special requirements you have. Then D-Search finds configurations that it thinks may be good potential starting points, which you then go off and you optimize some more. Well, it works well for easy jobs. I've run it on a lot of them. And that's why I asked Dave for a really hard job. So he originally suggested I do 11 elements. He hadn't tried doing fewer elements yet. So I give that one a try. Here are the specifications. There's the N. You've already seen these NA, field of view, and so on. 2 wavelengths, 2 glass types. And I ran D-Search. OK, drum roll, you ready for this? It came up with this lens. And with the BQA combination, it was 25 minutes. Well, that's pretty reassuring. Here's what the program tells you. These are the 10 best configurations. And several of these are actually quite good, even without any further optimization. So that was too easy. I was looking for a hard problem. So I tried 10 elements, 9 elements. It wasn't until I tried 8 elements, now the problem got hard. And this is what I was looking for, a hard problem, remember. Well, I couldn't let myself be defeated by a mere human being, so I decided to pull out all the stops, do a random search, 5,000 cases, full optimization of each case, 60 passes, simulated annealing, the slowest possible combination. But of course it works. Here's what happened. I ran it for 8 hours, came up with this lens, and the MTF is really quite good. But if the contest were to end now, I would declare Schaefer the winner, because I'm not going to wait 8 hours for my answers. In order to be practical, this process has to run in just a few minutes. Otherwise, I'm not going to use it. So now then, the problem is how to make it practical. I told you we have some fast and slow options, so let's try some of those. You can reduce the number of cases to try. That means use the binary search, not random. You can make each case run faster, either with fewer cycles or else do a quick screening pass. You can bypass cases that are obviously no good. This is like a filter. If one of the cases is all flint glass, you know that's not going to work, so don't waste time on it. You can do annealing. It works better, but it takes longer. I note now that the program does honor the multi-core declaration. If I run this on my 8-core machine, it runs 8 times faster, which is kind of nice. The timings I'm giving in this talk are all for a single core, just so you'll know. I mentioned the quick mode, and the way that works is it makes a temporary merit function with only 3rd and 5th order aberrations plus 3 rays. And because you're not tracing a zillion rays, it runs very quickly. And then you pick the best ones and you go back and you pound on those some harder. But maybe the best quick one is not best when you consider higher orders. Randomness also plays a role. That is, how do we know this metaphor of a mountain is really accurate? Maybe there are nice valleys you can't get to just by sliding down from a mountaintop. Well, what did we learn? Let's study this problem some more. This is a plot of the statistics of that 8-hour run. On this axis is the logarithm of the merit function, and a value of 0 would be perfect. And on this axis is the number of those cases that had that merit function. Now look at here. Of all those many cases, 189 wound up with this value of the merit function, which tells me they probably wound up with the same lens. In other words, this lens appears to be in a very broad valley. You can get there from a lot of different places. But it's not a very good valley. It's not very deep. I suspect that every one of these peaks is a different local minimum, different valley. And over here at the end, that's the guy you're after. That's the solution. And on this plot, you see why lens design is hard. Because you're looking for this solution over here, and you have to try to avoid getting stuck in any of these other valleys. That's why lens design is hard. Okay, well, let's use our head and not our hammer. I don't like this 8-hour run. I tried the binary search method, and my first results were not as good as Dave's lens, and we can ask why. Now remember, the binary number determines what direction you head down from the top of the hill. But you can ask, how far from the top should you start? And does it matter? Well, look at here. This is your plane, this is your mountain here, plane parallel plates on top. If you were to jump down a little way and start sliding down the mountain, you're going to go behind this ridge and you're going to go off in that direction somewhere. If you were to jump farther and land here, you're going to come down this valley and find a different valley, to find a different minimum. So yes, it looks like the distance you start off may indeed affect which valley you wind up with. So knowing that, I did another design study, running D-Search many times, but I told the program, only look at this construction. This was Dave's construction. And I varied the initial radius. That is, you start with almost flat or a little bit curved or more curved. And I found a very interesting plot here. There's a region here where the initial radius is not very important. You get a good solution for a whole lot of different values. But if you start with a steeper radius or a much more shallow radius, you get into trouble. And this makes sense, because in either of those conditions, the initial lens will probably show ray failures. That is, rays won't even trace through the lens. And now the program can recover from ray failures, but in the process, it has to change the construction. And it can move you out somewhere in design space. You might be near a good minimum. You might be near a lousy one. And that's why this is chaotic. It bounces all over the place when you're out of this region. So I'm going to call this a sweet spot. And I'll say to make the process work well, this is about 600 millimeters, which is about 6 times the focal length. So let's make a rule. The process works best if the initial radius is about 6 times the focal length. Okay, we have several options. Some are fast, some are thorough. There's reasons why they might work. There are reasons why they might not work. And the only thing we can do is try some out and see. So let's try some. Here's a combination, random 1,000 cases, quick mode with annealing. This took only 11 minutes with an 8-element lens. Hey, that's pretty good. What can the binary mode do? Well, here's one I ran binary mode, full optimization plus annealing. This took almost an hour, which is longer, but it's a little better design. And here's more. I was pushing this now faster and faster to see how far I could go. Binary full with annealing, only 10 cycles of optimization to try to speed it up. And after 16 minutes, it came up with this lens. All of these, by the way, I've been optimized some more after I got the configuration. So you can trade off the fast and slow options. Here's a surprise. 20 quick cycles, 20 cycles of optimization, some annealing, 4.8 minutes, and it's also an excellent lens. But most of the very fast runs were not this good, and we can ask why. There seems to be some kind of a conservation law here, because if I do a run that takes 20 minutes, it usually came up with a pretty good lens. If I do a run that takes 5 minutes, it works about 1 time out of 4. So it looks like you need a certain amount of labor just to find these solutions. And we can ask why those fast runs don't always work very well. And here's a possible explanation. Suppose that in the interest of speed, we're going to say we'll run it for 20 cycles and then we'll weed out the bad ones. Well, here's a lens after 20 cycles. It has this merit function. And here's a different lens after 20 cycles. It looks worse. So I'd probably throw that lens out. I'd weed it out. Whereas, in fact, if I let it run some longer, it turns out to be the better lens. So here's a case where the acceleration method might not work. Okay, we have these techniques. The binary search might miss a good configuration. The quick mode, well, third and fifth order design, but maybe the higher orders won't be correctable. Fewer cycles can be misleading. We can filter out the lemons, and that seems to be a pretty good trick. I don't see too many disadvantages to that. In fact, we can use some optics knowledge. If you're doing an 8-element lens, a skilled designer will be able to predict it'll probably have 2 or 3 flint elements. So you can put in a filter, only look at those, which rules out most of the other ones. And this runs very quickly then. So you've managed to speed the process up considerably, and there's not much of a penalty for that, except, of course, you won't get a design that has 4 flint elements. So that seems to be a pretty good practice. Here's a good combination. Binary, full optimization, anneal, but filtering 3 flints, and that's a real fast run now. We've got some pretty good results out of a fast run. But we have to ask, is this cheating? Remember, this is a man versus machine contest, right? And I just assumed that, well, 3 flints is going to be the way to go. That's putting in some optics knowledge. Is that cheating? Well, I'm going to assume that the user has some knowledge of optics, so I'm going to let that slip under the wire. This is okay. That's okay. The machine, we'll let the machine take credit for that. The most varied results I got resulted either from a random search or the simulated annealing. And this is instructive because neither one is purely deterministic. And that tells us something. Maybe that metaphor of a mountain is not appropriate, or is not as appropriate in all cases. But if it's not a mountain, what is it? So here's a new metaphor, a World War I battlefield. Suppose you're sliding down from the mountain and you land in this trench and you're going zigzagging around. You can't see a great solution over here in this crater. But if you're over here and you run the simulated annealing, now you can climb over that hill and very likely you will fall into that crater. So that would explain our results. Just sliding down from a mountain cannot always get you into a deep crater. Random search can do it. Simulated annealing can do it. And the best way I found to run the program seems to be binary search, quick mode. It's worth a try because it's really fast. Filter out the lemons, do some annealing at the end. Random search if all else fails. And, of course, run the multi-core computer if you have one. Okay, here's a summary of our contest. On top, this is the human design by Dave Schaefer. These are 4 of the designs that I've showed you. Okay, all different. And here's some, the faster runs produce these designs. They're also very excellent. Here's the fastest run that I got any success with. And I want you to look at this. As I was researching this problem, I kept finding more and more solutions. Every one of these lenses is as good or better than Schaefer's design. Every one. And here's 2 more. Now I'll note that a human would probably stop as soon as he reached any of these solutions. He'd say, hey, I met the requirements, I'm going fishing. Whereas design search can give you a lot more possibilities, and that's useful. Okay, that's the 8-element design. Now what about 7 elements? This is where Schaefer really found that was as far as you can push it. Now you recall my goal in this whole exercise was to break the program. Well, success, it broke. I ran many cases running the same input I had before, but asking for 7 elements instead of 8. And the lenses that came back were not as good as Schaefer's lens. And I was about to give up, but I said, wait a minute, I know there's a solution because Schaefer found one. And then I got smart. I found adjusting the aperture weight works. Now let me explain that. When we optimize a lens, we trace a bunch of rays. We usually put a higher weighting factor on rays near the center of the pupil than we do rays near the edge. And that's a user-adjustable number. How much different should they be? And I found that if I increase that difference a little bit, now Schaefer's lens pops right out. But I'm going to score this round for the human for 2 reasons. One, as I said, I would have given up if I didn't know that solution exists. And secondly, I had to use some optics knowledge, which makes sense. If you take a lens out, you know it's going to be harder to correct rays near the edge of the aperture. So if you reduce the weight on those and you correct the rays where you can correct them and get what you can out of that design, you get the best you can do. But a naive user probably wouldn't have thought of that. So in a purely man versus machine contest, I'd say the man won this one. The machine lost. Okay, so here's the score. Round 1, the steam drill wins 23-1. Round 2, the human wins 1-0. And the winner is, hold your breath, well, it seems to be a draw. David Schaefer is impressed that a mere PC can sometimes do as well as a human. And the steam drill is impressed that a mere human can do a design that's a challenge for the best algorithms. But one thing is certain. If John Henry had used his head instead of his hammer, he would have applied for a job running the steam drill. Right? And would have enjoyed a comfortable retirement. Thank you. That was the talk that Dave and I gave at the SBIE meeting. Let me move on now to a related topic, but a little different. Wouldn't it be wonderful if you could grow a lens? I don't mean the biological kind. It is possible, at least mathematically, using an idea developed originally by Dr. Florian Boschort. He teaches at TU Delft in the Netherlands. He came up with an idea he called the saddle point build method. And I'll explain how this works. Okay, first of all, what's a saddle? Well, if this is the horse, and that's a cowboy, the saddle is the thing that comes in between the horse and the cowboy. Or to put it mathematically, it's a curve that goes up in one direction and down in another. And Florian's idea was that if you're in a local minimum, it says any change you make makes things worse. But if you can add some more degrees of freedom to the lens, now maybe one of those will go downhill. And the way he's drawn it in 3 dimensions, he can envision getting 2 better designs going in 2 different directions. I think this is a somewhat simple-minded picture because we're not talking about 3 dimensions now. We're talking about 30 or 40 dimensions, and who knows what a saddle point looks like in that space. Anyhow, the idea is intriguing, and I thought I'd program that and give it a try. So what do we do? The way to add variables, you don't want to disturb the merit function. One way is to add a thin element of almost 0 power. In other words, here's an element. I'm going to add a thin shell, shown exaggerated here. If the power and thickness are all 0, then the paths of the rays don't change. So the merit function doesn't change, but now you have 5 new degrees of freedom. Okay? So what you do, add a thin shell to each side, negative and then positive, optimize each case, and then you select the best one. Now you've added 1 element to the lens, and you iterate, adding elements one at a time this way. I'm going to show you a movie. This is a saddle point build, I call it. And we're going to start out with nothing in this case, in which case the program just puts in a singlet because it's got to start somewhere. And what you're going to see, here, this is the input, saddle point build, 5 elements, F number, and so on. There, it's got 2 elements. Now it's adding a shell here, it's adding a shell there. And it's going to add a shell there. Finds the best combination. Now it's got 3 elements, and it's going to try another shell to make it 4 elements, and so on. It's going one surface at a time, adding these shells. They turn into lenses. This is in real time, by the way. And then it's when it gets the best 4-element design, it'll start with that and try adding elements to build it up to 5 elements. Now it's trying element number 5. So it adds an element in front and back. So you're watching a lens grow from nothing. And I don't think, no one else has ever done this before. And you're one of the first audiences who were ever able to see this actually happen. And now it's almost done. It's going to add a shell here in the end and turn that into a lens. And here we are. So there's a 5-element lens. It's not a bad design, starting from nothing. I showed this movie to some of Florian's students over in TU Delft, and their faces were getting longer and longer. And one of them said, "We'll be out of a job." And I pointed out that these global optimization techniques don't always work. So we still need you. It's okay. Now let me finish my talk by describing a real-life example. Now this happened during the Cold War. I was working at ITEC Corporation on a project called the Corona Project. It's recently declassified, so now I can talk about it. I couldn't do that for many years. And their job was to design spy cameras. Those flew over Russia, taking pictures of a satellite, and then it would eject the film, it would come down to Earth in a parachute, and an Air Force jet would catch it in midair, bring the film back to the U.S. where they developed the film and see what the Russians were up to. Now, this is spooky stuff, right? This project, needless to say, this was a classified project. You can probably guess that much, right? You never saw classification like this. This project was so classified that the classification was classified. In other words, nothing was stamped secret. Okay? Of course, we all had security clearances, but the clearances were classified. They didn't tell me I had a clearance while I was working there. Oh, this was spooky stuff. And if a group of engineers had to go out to the West Coast to meet with a customer, they couldn't all fly on the same airplane, and they couldn't fly to the right city. They had to fly to a different state, get on a train, and go to where the meeting was, because those nasty Russians were watching, and they didn't want them to know what they're up to. Now, this is really, it was fun. That's spooky stuff. Okay, they were designing these aerial camera lenses. Here's an example. This is a Petzval lens. You've heard that name already. I designed a 9-inch Petzval, which I don't have a picture of, but it looks about the same as this 13-inch. Petzval lens has a positive group here, a positive group partway to the image, and then they added some field lenses at the end to get the best correction. they wanted the best resolution they could possibly get. This was designed by some experts. They picked out the Petzval configuration because it is intrinsically better corrected for what we call secondary color. Okay? And this is what they did using the 1960s technology. They had a computer. The program was kind of primitive. Now, I was wondering, what can my modern design search program do given the same requirements? So I made up this thing here. I'm saying here's the wavelength. This kind of works in the red, 8 elements, F number, and so on. Gave it the requirements, and I ran design search for several minutes, and then I took the best design and I went and optimized it some more. And this is what I come up with. And look at that. There's a positive group in the front, a positive group in the middle, a little more airspace, and corrector lens at the end. The program has found the Petzval lens just by brute force number crunching. And these are the transverse aberrations. Here are the wavefront aberrations. Now, there's an interesting story. This story gets interesting when you see what I did after running design search. Here's the results. This is the 1960s technology. Here's what SYNOPSYS plus design search did. But in order to get that kind of performance, I had to do apply some optics knowledge after the number crunching was done. What I was after is what's called super achromat performance. This is an idea that was published by Max Hertzberger in the early 60s. The way it works is this. If you have one lens element, you can make one color focus at an image. If you have 2 elements with the right kind of glass, you can make 2 colors focus there, but there's a residual in between. If you have 3 elements with the right kind of glass, you can make 3 colors focus right there, and the residuals are much smaller. That's called an apochromat, and it's usually the best correction that most people ever hear of. But Max Hertzberger published a theory where he says if you pick the 3 glasses with a different rule, it's possible to make 4 colors come to focus at the same place. Remarkable idea. So I said, let me apply that technology to this design to see how well I can make it work. Now, this is the normal shot glass map. And all these pictures, by the way, are straight out of my program. I have the best optics design program in the world, and it can make pictures like this. End of commercial. Okay, this is the shot map. We're showing the index plotted here. And in this axis is what's called the Abbe number. It's a measure of the dispersion of the glass. And here's a picture of what the problem is. This is the index of one of the glasses as a function of wavelength. And look, it's a curved line. It's more curvy in the blue than in the red. It's the curviness of that line that makes color correction so difficult. Because you can match the slopes with the right index, but the curves never match, and so you get a residual, which is very hard to correct. And that's where Max Hertzberger came up with his theory, the super achromat, published in 1963. And he decided that if you plotted P star versus P double star, as defined this way, then any 3 glasses that lie on a straight line can correct 4 wavelengths. Well, I optimized this lens, first of all, letting the glass float, letting the program decide where on the glass chart it wants to be. And just by chance, 4 of them came out to be very close to a straight line. So I put those glasses on the line and optimized letting the other glasses move around. In other words, optimize varying the model, assign some to a suitable line, optimize with the remaining glasses, and then the last step, I had to select real glasses whose partials in the red are similar to the model. Let me explain how that works. Optimize with those. Here, this is another plot from my code showing what we call the deviation from the normal line, and this is in the red where we're interested here. The normal line is the way certain very typical glasses behave, and other real glasses can be more curvy or less curvy. And this is a plot that gives you a picture of that. Now, for example, in this area, here's a glass where it's this deviation is negative, and this glass has a deviation that's positive. Well, one of the glasses that the program wanted from its glass model was right in this area, and it wanted a slight positive deviation. Well, gee, there's a glass right there that matches that pretty well. So I fixed it to that glass and did the same thing for the others. And in that way, I got a design which is almost perfectly corrected for color. I have to ask why the people at iTech didn't do that, because this paper Hertzberg was published before they were doing these lenses, but they apparently didn't know about it or didn't choose to use that information. Anyhow, now, the process I've described turns out to be just the opposite of the classical procedure. Because remember, the classical one said start with algebra, get the shape of the lens, and then you trace lots of rays and perfect the image. I did the opposite. I used brute force number crunching to come up with the configuration, and then used optics theory to perfect the design. So that's we just turned things around and did things all completely backward. Okay, where do I stand? Well, I have one foot in both camps. Understand your lens, plus let the computer do the number crunching. In other words, put the genius on the computer. Like that. Thank you.
Questions?